Welcome to this coding walkthrough. Today, we'll explore problem number 1813, sentence similarity 3. This problem challenges us to determine whether two sentences can be made similar by removing some words. Let's dive in and analyze the approaches to solving it. For instance, examples like Hello World, LeetCode, or I am happy all qualify as valid sentences. For example, the sentences Hello my name is Jane and Hello Jane are considered similar because we can insert the words my name is between hello and Jane in the second sentence to make it match the first. Similarly, LeetCode is great and LeetCode is are similar because we can simply add the word great at the end of the second sentence. In this problem, we are working with two strings, referred to as sentence 1 and sentence 2. A sentence is defined as a sequence of words separated by single spaces, without any leading or trailing spaces. Each word in these sentences consists exclusively of uppercase or lowercase English letters, and there's no punctuation involved. The goal is to determine if these two sentences are similar. Sentence similarity here means that by inserting an arbitrary number of words, possibly 0, at any position in either sentence, we can make the two sentences identical. Given this, we need to return true if the two sentences are similar, and false otherwise. Now, let's discuss the expected input and output for this problem. The input consists of two strings, sentence 1 and sentence 2, each representing a sentence. The length of these sentences ranges from 1 to 10,000 characters. The task is to determine if the two sentences are similar, as defined earlier. If they are, we return true; if they are not, we return false. Let's look at some examples to clarify this further. In the first example, we have sentence 1 is my name is Haley and sentence 2 is my Haley. The output here is true, because we can insert the words name is between my and Haley in sentence 2 to make it identical to sentence 1. Here's another example. For sentence 1, we have of, and sentence 2 is a lot of words. In this case, the output is false. Even though we can insert or remove words, it's not possible to transform one sentence into the other to make them identical. Let's consider one more example. If sentence 1 is eating right now and sentence 2 is simply eating, the output is true. This is because we can insert the words right now at the end of sentence 2 to make it match sentence 1 exactly. To conclude, let's review the constraints and edge cases. Both sentence 1 and sentence 2 consist of uppercase and lowercase English letters and spaces, and their lengths are between 1 and 10,000 characters. Words within the sentences are separated by single spaces only. Some important edge cases to keep in mind include sentences with only one word, where we need to check if the other sentence can be made equal by inserting or removing words, sentences that are already identical, which should return true, sentences with no overlapping words, which should return false, and sentences that differ by just one word, where we need to check if the difference can be resolved. Understanding these nuances will help us work out a solution efficiently. To tackle this problem, we first consider two different approaches. The first is a brute force method, which involves iterating through all possible ways to split both sentences into three sections: a prefix, a middle, and a suffix. The goal here is to check if the non-middle portions of one sentence match the prefix and suffix of the other. While this approach is straightforward and easy to conceptualize, it is not efficient. Its time complexity is n cubed, where n represents the combined length of the sentences. This inefficiency arises because we have to examine all valid split points for both sentences and repeatedly compare substrings. The second approach is a significant improvement. Using a two-pointer technique, we align words from the start and end of both sentences, comparing them until we find mismatches. Once mismatches occur, we check whether the remaining unmatched sections of the sentences can still align. This method is much faster, with a time complexity of n, as it ensures each word is traversed only once. The two-pointer approach is both conceptually elegant and highly efficient for this problem. Now, an alternative method worth considering is the sliding window approach. This technique involves finding the largest matching prefix and suffix between the two sentences by manually manipulating substrings. While it can be implemented iteratively, it tends to require more manual handling of substring operations compared to the two-pointer method. This makes it slightly less clean and more error-prone, especially when dealing with edge cases. Ultimately, the two-pointer approach emerges as the most intuitive and efficient solution. By aligning words from the start and end, we can efficiently determine if the sentences share matching prefixes and suffixes, leaving only the middle section to validate. The key insight here is that the problem boils down to ensuring the unmatched middle sections, if any, are compatible. This eliminates the need to explore all possible splits exhaustively, saving both time and computational effort. Additionally, the two-pointer approach naturally handles tricky scenarios, such as when one sentence is entirely a prefix or suffix of the other, making it both robust and efficient. Finally, let's evaluate the trade-offs between these approaches. The brute force method is conceptually simple but impractical due to its n-cubed complexity, which makes it infeasible for larger inputs. The sliding window approach, while more efficient than brute force, introduces additional complexity in implementation and struggles with certain edge cases. On the other hand, the two-pointer method offers an optimal balance of clarity, efficiency, and correctness. With a time complexity of n and straightforward implementation, it avoids the computational overhead of brute force methods and the manual substring management required by sliding windows. This makes the two-pointer approach the clear choice for solving this problem effectively and cleanly. To solve the problem of determining if two sentences can be split into three parts, prefix, middle, and suffix, we start by defining the input and the scope of the problem. Let's call the two input sentences S1 and S2. The objective is to divide each sentence into three sections, the prefix, middle, and suffix. For S1, we'll label these as P1, M1, and S1 respectively, and for S2, as P2, M2, and S2. The key requirement is that the prefixes, P1 and P2, should match exactly, and the suffixes, S1 and S2, should also match. The middle sections, M1 and M2, can differ. Next, we iterate over all possible ways to split S1. For each possible split point I, we define the prefix as the substring up to I, the middle as the substring from I to some later split point j, and the suffix as everything after j. By systematically evaluating all valid combinations of I and j, we ensure that we exhaust all possible ways to partition S1 into the required three parts. Similarly, we iterate over all possible ways to split S2. For each potential split point k, we define P2 as the substring up to k, M2 as the substring from k to some later split point L, and S2 as everything after L. By evaluating all valid combinations of k and L, we generate every possible partition of S2 into prefix, middle, and suffix. Once we have these splits for both sentences, we check the matching conditions. Specifically, we compare the prefixes, P1 and P2, and the suffixes, S1 and S2, for equality. If we find any combination of splits where both the prefixes and suffixes match, we can conclude that a valid split exists and return true. If no such match can be found after examining all possible splits, we return false. This exhaustive approach ensures that we explore every possibility, but it is computationally intensive. Now, let's analyze the complexity of this brute force approach. If the lengths of S1 and S2 are n and m respectively, the number of ways to split S1 into three parts is approximately n squared, because we select two split points, I and j. Similarly, splitting S2 involves m squared, combinations of k and l. For each pair of splits, we compare substrings, which can take up to k time in the worst case, where k is the length of the substring being compared. This results in an overall time complexity of n squared times m squared times k, which is quite expensive for longer sentences. However, there are some key insights that can help us optimize. First, the brute force nature of the approach guarantees that we explore all possibilities. Second, the problem fundamentally revolves around matching prefixes and suffixes, which simplifies the problem by allowing us to disregard the middle sections, M1 and M2. This means we can focus solely on aligning the boundaries. Finally, optimization techniques like dynamic programming or hashing, such as Rabencarp, can reduce redundant substring comparisons, making the algorithm more efficient. To implement this algorithm, we rely on basic data structures and operations. First, the sentences themselves, S1 and S2, are stored as strings. The substrings, such as P1, M1, and S1, are extracted using slicing operations. Additionally, we use integers to represent the split points I, j, k, and l, which define the boundaries of the substrings. The key operations involve substring extraction, which is efficient with slicing and operates in k time for a substring of length k. Another key operation is substring comparison, which involves a character-by-character check and also takes O(k) time. The iterative splitting process, where we evaluate all possible split points, is implemented using nested loops, leading to quadratic complexity for each sentence. Together, these data structures and operations provide the foundation for implementing the brute force solution. Finally, it's important to consider edge cases to ensure the solution is robust. One scenario is when the two sentences are completely different, with no common prefix or suffix. For example, if S1 equals ABC and S2 equals def, the result is immediately false. Another case is when the sentences are identical. If S1 equals S2, we can trivially match the entire sentence as the prefix and suffix, with an empty middle section, making the result true. Partial overlap is another edge case, where only part of the prefix or suffix matches. For instance, if S1 equals abxis and S2 equals abkavwas, we need to carefully evaluate the boundaries to determine a valid split. Lastly, we handle empty sentences. If either S1 or S2 is empty, the result depends on the structure of the other sentence. For example, if S1 equals and S2 equals prefix-affix, there's no way to align the two, so the result is false. Considering these edge cases helps ensure the algorithm handles all possible inputs correctly. This implementation solves the problem of determining if two sentences are similar by analyzing their prefix and suffix matches. The function first splits the input sentences into lists of words. To simplify handling, it ensures the shorter sentence is always processed first. The algorithm then iterates to match words at the beginning, prefix, and the end, suffix, of both sentences. Using two counters, I and j, it counts how many words match from the start and end respectively. Finally, the function checks if the total matched words, i.e., prefix plus suffix, cover all words in the shorter sentence. If so, the sentences are deemed similar. This approach efficiently handles edge cases, such as one sentence being completely contained in the other. The time complexity is O(n), where n is the length of the longer sentence, as we only traverse the sentences once for prefix and suffix matching. Here, we have the Java implementation for the problem. We start by defining a class called solution and a method named rSentenceIsSimilar that takes in two string inputs, sentence 1 and sentence 2. The first step is to split these sentences into arrays of words using the split method, so words 1 and words 2 now contain the individual words from each sentence. To simplify the logic for comparison, we ensure that words 1 represents the shorter sentence. If words 1 is longer than words 2, we swap the two arrays. This guarantees that our comparisons handle the shorter sentence first. Next, we initialize two indices, I and j, to 0. The variable I is used to find the matching prefix, so we iterate through both arrays and increment I as long as the words at the same index in both sentences match. Similarly, j is used to find the matching suffix. Starting from the end of the sentences, we increment j while the words at the corresponding positions in reverse order continue to match. This way, we identify the largest prefix and suffix that are common to both sentences. Finally, we check if the sum of I and j, which represents the total length of the matching prefix and suffix, is greater than or equal to the length of words 1, the shorter sentence. If this condition is true, it means the shorter sentence is entirely covered by the prefix and suffix matches, and we return true. Otherwise, we return false. This implementation ensures that the comparison is efficient and handles sentences of varying lengths seamlessly. The method then concludes, and with this, we have a complete solution to determine if the two sentences are similar based on the given criteria. To start solving this problem, we'll look at the first example. Here, the input sentences are I love coding and I love coding and algorithms. The first step is to split these sentences into words, which gives us two lists. Words 1 is I love coding and words 2 is I love coding and algorithms. Since the algorithm requires that words 1 be the shorter of the two, we check their lengths. In this case, words 1 has 3 elements and words 2 has 5, so no swap is needed. Next, we find the prefix match by comparing elements from the beginning of both lists. I matches in both lists, followed by love, and finally coding. At this point, the prefix match covers all elements in words 1, so we record the prefix match length as I equals 3. Now, we move to finding the suffix match. Since the prefix match already covers all elements of words 1, there's no need to check for additional suffix matches. This means the suffix match length is recorded as j equals 0. We then check the total coverage by summing I and j, which gives us 3. Since this matches the length of words 1, the output for this example is true. This shows that sentence 1 is indeed a subsequence of sentence 2, even when additional words are present in sentence 2 beyond the common sequence. In the second example, the inputs are coding is fun and I love coding. After splitting the sentences, we get words 1 as coding is fun and words 2 as I love coding. Both lists have the same length, so no swap is needed. Next, we attempt to find the prefix match by comparing elements from the start. However, the first elements don't match, coding is not equal to I. As a result, the prefix match length is I equals 0. We then look for a suffix match by comparing elements from the end of the lists. Here, the last elements also don't match, fun is not equal to coding. This means the suffix match length is j equals 0. When we check the total coverage by adding I and j, we get 0, which is less than the length of words 1. Therefore, the output for this example is false. These sentences don't have enough overlapping elements to make sentence 1 a subsequence of sentence 2. In the third example, the input sentences are I love and I love coding. Splitting these gives words 1 as I love and words 2 as I love coding. Since words 1 has 2 elements and words 2 has 3, no swap is necessary. We then proceed to find the prefix match. Comparing elements from the start, I matches in both lists, followed by love, which also matches. This means the prefix match length is I equals 2, as all elements of words 1 are part of the prefix of words 2. For the suffix match, no further comparison is needed because the prefix already covers all elements of words 1. As a result, the suffix match length is recorded as j equals 0. When we check the total coverage by adding I and j, the result is 2, which equals the length of words 1. This confirms that sentence 1 is a subsequence of sentence 2. Therefore, the output for this example is true. This demonstrates how partial matches, where all words in the shorter sentence are covered within the prefix of the longer sentence, can still yield a positive result. In this problem, the time complexity of our algorithm comes from several distinct steps. First, we have the splitting of the two input sentences into word lists using the split function. This process involves scanning through every character in each sentence to identify spaces and create substrings, which gives us a time complexity of O(m) for sentence 1 and O(n) for sentence 2, where m and n are the lengths of the respective sentences. Next, there's a quick check to determine the order of the sentences based on their lengths. The comparison if len, words 1, len, words 2, and the swapping of references both operate in constant time, O(1). After that, we move to the prefix matching step, where a while loop iterates over the words in the shorter sentence. In the best case, the loop breaks early, which is O(1), but in the worst case, it processes all the words in the shorter list, resulting in OK, where K is the length of the shorter sentence. These steps collectively set the stage for analyzing the rest of the algorithm's time complexity. Now, focusing on the suffix matching step, it operates similarly to the prefix match but iterates in reverse over the shorter sentence. Again, in the best case, the loop terminates after just a few iterations, while in the worst case, it processes all K words, where K is the length of the shorter sentence. This step also has a time complexity of OK. After the prefix and suffix matches, there's one final check to ensure that the combined matches cover the entire shorter sentence. This condition, I plus j equals len, words 1, is a simple arithmetic comparison that takes constant time, O(1). Combining these steps, the overall time complexity is determined by the dominating terms, which are the string splitting steps, O(m) plus n, and the prefix and suffix matching, O(k). Since k is at most the length of the shorter sentence and the lengths of the word lists are proportional to m and n, the overall time complexity simplifies to O(m) plus n. Turning to space complexity, the most significant contribution comes from splitting the sentences into lists of words. When split is called, it creates new lists, words 1 and words 2, with a number of elements corresponding to the number of words in the sentences. If W1 and W2 represent the number of words in sentence 1 and sentence 2, respectively, then this operation requires W1 plus W2 space. Additionally, the algorithm uses two integer variables, I and j, to track the indices for the prefix and suffix matches. These variables require only constant space, O1. The swapping of references for the word lists is also a constant time operation, as it does not involve duplicating any data. Altogether, the dominating factor in the space complexity is the storage of the word lists, which makes the overall space complexity O, W1 plus W2. When comparing this optimized approach to a naive solution, the improvements are significant. A brute force method might attempt to compare every possible substring of one sentence to every substring of the other to check for matches. This would involve performing O, open parenthesis m plus n close parenthesis squared, comparisons in the worst case, resulting in a time complexity of O, open parenthesis m plus n close parenthesis squared. By contrast, the optimized algorithm avoids unnecessary comparisons by leveraging the natural order of words in the sentences. It focuses specifically on matching the prefix and suffix, which greatly reduces the computational workload. As a result, the optimized solution achieves a time complexity of O, m plus n, and a space complexity of O, W1 plus W2. These improvements make the algorithm much more efficient, especially for longer sentences. Looking at the best, average, and worst case scenarios, we can see that the algorithm consistently maintains its efficiency. In the best case, the sentences might be identical or completely disjoint, allowing the prefix or suffix match to terminate early. Here, the overall time complexity is dictated by the string splitting step, which is O, m plus n. In the average case, the prefix and suffix match loops typically process some subset of the words, but the dominant factor still comes from the string splitting, keeping the complexity at O, m plus n. Even in the worst case, where one sentence is a substring of the other with a large overlapping prefix and suffix, the loops will process all words in the shorter sentence. However, since the splitting step and the matching loops are proportional to the sentence lengths, the complexity remains O, m plus n. This is mathematically evident when breaking down the operations, as the string splitting is O, m plus n, the prefix and suffix matching is O, k, and all other operations are O, 1. Therefore, the overall complexity is consistently O, m plus n, across all cases. When tackling this problem, there are some common mistakes to watch out for. First, failing to handle edge cases, like empty strings, can cause your solution to break in scenarios where one or both input strings are empty. Always account for these possibilities to ensure your implementation is robust. Another pitfall is incorrectly slicing strings. This often happens when you miscalculate indices or use improper slicing syntax, leading to off-by-one errors. It's essential to validate your index logic, especially when working with substrings or comparing prefixes and suffixes. Additionally, overlooking constraints on string lengths can be problematic. For instance, ignoring maximum string length constraints might result in inefficient solutions that exceed time limits. Always use constraints as a guide to shape your approach. Finally, avoid inefficiencies caused by repeated operations. For example, recomputing prefixes or suffixes multiple times instead of caching the results can slow down your solution significantly. Techniques like memoization or pre-computed arrays can help optimize your implementation and save valuable computation time. Another common mistake is assuming that strings are case-insensitive. Some problems may require strict case-sensitive comparisons, while others may not. The key is to carefully read the problem prompt to understand whether case sensitivity matters and adapt your solution accordingly. Now, when it comes to interviews, there are a few key insights to keep in mind. Pattern matching is often at the core of string problems, whether it involves splitting strings, comparing prefixes and suffixes, or finding substrings. Breaking strings into manageable pieces can simplify your approach. Efficiency is also crucial. While brute force methods might work on small inputs, they usually fail to scale for larger constraints. Think about optimizing your solution and analyzing its time complexity. It's also important to clarify requirements during the interview. For example, confirm assumptions about the input, such as whether it only contains lowercase letters, is ASCII-based, or involves case sensitivity. Finally, always test thoroughly. This includes edge cases like empty strings, single-character strings, or strings with vastly different lengths, as these are common scenarios that can reveal potential bugs in your solution. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 567, Permutation in String, focuses on substring matching using the sliding window technique, which is a commonly applicable strategy. Similarly, LeetCode 28, find the index of the first occurrence in a string, involves substring search and is often tackled with efficient algorithms like the Knuth-Morris-Pratt algorithm. LeetCode 5, longest palindromic substring, is another relevant problem that explores substring properties and uses dynamic programming techniques to find the solution. Lastly, LeetCode 76, minimum window substring, introduces more advanced substring searching methods, leveraging sliding window optimizations. By studying these problems, you'll notice recurring techniques and strategies that can be applied across a wide range of string-related challenges, helping you build a stronger foundation for solving similar questions. Now, let's discuss alternative approaches and the trade-offs involved. A brute force approach involves iterating through all possible splits of both strings and comparing their components. While this method is straightforward to implement, it's highly inefficient for larger inputs, often with a time complexity of O, in superscript 3, or worse. On the other hand, a sliding window approach dynamically compares prefixes and suffixes, offering a much faster solution with a time complexity of O, n. However, this method requires careful handling of window adjustments to ensure correctness. Another option is leveraging hashing or pre-processing. By pre-computing hash values or prefix/suffix arrays, you can significantly speed up comparisons. This approach improves efficiency but comes with trade-offs, such as increased memory usage and additional setup time. Each of these methods has its strengths and weaknesses, so the best choice often depends on the specific constraints and requirements of the problem you're solving. Great job following along. In summary, we tackled sentence similarity 3 using a brute force approach. We discussed its complexity and key takeaways. Remember to practice similar problems to strengthen your understanding. Thanks for watching, see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!